Hello and welcome to week 4, lecture 2. We're going to be talking about friction in circular motion. This comes from chapters 5-3 and 5-4. It's going to go friction, an example of friction, and then dynamics of uniform circular motion and an example. So we've talked about Newton's laws and how an object experiencing no forces will either remain at rest or continue moving at a constant speed. But we also know from experience that if we roll a ball across the floor, it will eventually stop moving and not just when it runs into a wall. That means there must be a force acting on it to stop that motion. That force is friction. Friction is a force that comes from the interaction of two surfaces in contact with each other. The surfaces catch onto one another depending on what they're made of. So rubber tire on concrete experiences more friction than rubber tire on it. And this just shows kind of the interaction between the two surfaces and the places where they kind of like get caught on each other. So static friction. This is friction that prevents an object from moving. So in our example, we have a block at rest on a table. Initially, it's just experiencing its weight force and normal force from the table. But then let's say we apply some horizontal force to it. That's this capital F here. Maybe we're pulling it, maybe we're pushing it. And what happens is that when we apply this force, static friction force also acts to oppose the motion. So our force would cause acceleration to the left, and that's why the friction force points to the right. So it acts to oppose the motion, the potential motion, really. And if we increase our force on the block, the static friction force also increases to remain equal and opposite to the force we're applying. So here we apply a larger force, that static friction force gets bigger to counteract it. And an even bigger force, an even bigger static friction force. This continues until we get to a maximum value of the static friction force, and then the block begins to move. And we have this equation for the static friction force. So the friction forces are given by like a lowercase f, sometimes a curly f. Static will have a subscript of f. And so generally speaking, the static friction force is less than or equal to the coefficient of static friction, that's what this mu is, times the normal force. And this less than or equal to just says the static friction force isn't bigger than it needs to be to counteract the force that it's experiencing. So like at this point here, it's definitely less than the coefficient times the normal force. And maybe at this point, it's at its maximum. Like it's the biggest the static friction force can get. And past this point, the object will begin to move. But again, the static friction force is just as big as it needs to be in order to prevent motion. Then we have kinetic friction. And kinetic friction is a constant value. It doesn't change based on the force acting on an object. And it acts opposite the direction of motion. It works to counteract that motion. So we have the static friction force equals the kinetic friction force equals the coefficient of kinetic friction times the normal force. And these friction coefficients depend on the two surfaces, and I have something on that on the next slide. But it doesn't matter if there's acceleration or how fast the object is moving, even if it's moving with constant velocity. As long as it's moving and the surface has friction, it's going to be experiencing the same kinetic friction force. And again, kinetic here just means because it's moving, whereas static means not moving. And this is some examples of coefficients of friction. rubber on concrete, steel on steel, dry or lubricated, wood on wood, wood on snow, ice on ice. And one thing I want you to notice is that the kinetic friction coefficient of kinetic friction is smaller than the coefficient of static friction. And that also means that the maximum static friction force is larger than the kinetic friction force. So the force needed to get something moving is gonna be smaller than the force needed to keep it moving. If that makes sense, because in order to get it moving, you have to overcome that maximum static friction. In order to keep it moving, you just have to overcome kinetic friction. Or actually, to keep it accelerating, you need to do that. And I didn't put this before. Before we had the static friction force without this mass here as less than or equal to, but when it has the maximum static friction, that's when it's equal to. Now we're going to do this sample problem 5-8. A block is at rest on an inclined plane, making an angle with the horizontal. As the angle of the incline is raised, it is found that slipping just begins at an angle of inclination of 15 degrees. What is the coefficient of static friction between the block and the incline? So we are going to tackle this problem. Okay. Zoom in a little bit. So I've drawn the situation for you. Block at rest on an inclined plane, making an angle with the horizontal. And I think we will just start with our free body diagram and kind of break down the problem more as we go. So again, just like last lecture, we're tilting our axes. This is positive X, this is positive Y. You are welcome to label this axis as positive X. I like to just keep them constantly like the same, but if you'd rather not deal with extra negative signs, you are welcome to do that. So we have our weight force pointing straight down, our normal force pointing straight up, and then we have this friction force, which is going to act opposite the direction of potential motion. So obviously our objects would go down the incline if it was able to overcome the friction. So that means friction needs to point up the incline. And then this is that theta, and we have the y and x components of our force. Okay. And we're going to do our sum of forces equation. Sum of forces in x. And at this point, the object is not moving yet. So there's also not acceleration happening. So we can say that this is equal to 0. And then static friction is in the positive x, so it goes first, and then we subtract the x component of the weight from it. And then in y, also 0, and that is the normal force minus the y component of the weight. So the thing we just learned is that the static friction force is less than or equal to the coefficient of static friction times the normal force. And the main thing here in this problem, because they talk about just begin slipping, that means we're kind of like right at the maximum value of static friction. So maximum, and that means it's equal to the coefficient times the normal force. So what we want to solve for is the coefficient. And so the first thing we can do in this equation, if we just add the y component of the weight to both sides, we see that the normal force is the y component of the weight, which is the weight times cosine of theta. Okay, so we have that, and then we can also, using the relationship here in the x direction, add the x component of the weight to both sides. So then we have the static friction force is equal to the weight times sine of theta. And the static friction force, as I said, is equal to the coefficient of static friction times the normal force, weight sine theta. But the normal force is weight cosine theta. So let's plug stuff in. Weight cosine theta equals weight sine theta. Look at that. Weight is on both sides, so we can get rid of it, and then we'll divide both sides by cosine of theta. So the coefficient of static friction is the tangent of theta. I'm pretty sure it said 15 degrees. Yeah. So tangent of 15 degrees, which is 0.27. So that is the coefficient of static friction in this situation. And a note, I didn't mention this, but friction coefficients do not have units. And also they should be less than 1 and not negative. I am pretty sure about that part. So briefly, we had an object on an incline. We're told it just begins to slip when the incline is at 15 degrees. So that's telling us that at 15 degrees is when it's at its maximum static friction force. We made our free body diagram, tilted. We did our sum of forces, and then we used them to solve for the coefficient of friction, which we found to be 0.27. Cool. Now we're going to go back to the slide. Okay. So now, dynamics of uniform circular motion. So as a reminder, in uniform circular motion, you can connect the net force to the velocity and the radius of the circular motion. So we get the net force is equal to mass times velocity squared over r, because in circular motion, the acceleration is given by v squared over r. So now I'm going to touch on 2 examples just to introduce them. We're not going to spend much time on them right now. We might go back to these ideas later in the quarter, but we'll see. So first example is the conical pendulum, named this way because it traces out a cone shape. So as it goes around the circle, makes a cone. And it's a pendulum that is free to rotate in a circle. To solve this problem, you actually would use cylindrical coordinates, which are the radial direction. So out from the center of the circle, the angular direction, so around the circle, and then the z direction up or down. So for example, we have components of the tension in the radial direction and in the z direction. The rotor is a carnival ride where you stand against the wall in this big cylinder and it starts to spin really, really fast. And you feel like you're sticking to the wall. And sometimes the floor will even drop away and you're just kind of like floating against the wall. And what's happening here is a combination of circular motion with the normal force, pointing toward the center of the circle. So the normal force is what is giving us that force towards the center for circular motion. And then we have friction force pointing up, the friction of the person's clothes and the side of the ride, to counteract their weight force. I think this has other names too. And I think we probably will come back to this one and do an example of it, but just not right now. Okay, so now this is an example of uniform circular motion that we will work with now, and we're going to do an example in a minute. But it's driving around a curve. So this side we have what is called an unbanked curve, which just means like a circle, but the road is flat. And that requires a force pointing toward the center of the circle. in order for that circular motion to occur. We've learned this. That force is actually the static friction force that prevents the object or car usually from sliding out of the circle. So I know we just introduced static friction, and I said static for not moving, and a car is moving, but the static friction force is the force preventing motion out of the circle or just kind of along this radial line of the circle. So the motion is like tangential or along the circle, but the static friction force prevents it from moving out of the circle, and that's what keeps it going in circular motion. And we have a free body diagram like this for a situation like this. The weight force pointing down, normal force pointing up, and then the static friction force is what's pointing toward the center of the circle. But on a banked curve, which is just like a curve with an incline, you don't need a frictional force to prevent the object from sliding out. Because we're on an incline, there's a component of the normal force that is in the radial direction or the direction toward the center of the circle. So now we're going to do this exercise from the textbook. It says a 2,400 pound or 10.7 kilonewton car traveling at 30 miles per hour, which is 13.4 meters per second, attempts to round an unbanked curve with a radius of 200 feet or 61 meters. What force of friction is required to keep the car in its circular path? What minimum coefficient of static friction between the tires and road is required? Okay. We're gonna write down what we know and potentially do some conversions and things we'll see. So the weight is given as 10.7 kilonewtons, which would be 10.7 times 10 to the 3 newtons, or 10,700 newtons. We might as well, just to be safe, also get the mass, which is the weight divided by gravity, and that is 1,092 kilograms. And then our velocity is 13.4 meters per second, and the radius of the circle is 61 meters. Cool. And then I'm just gonna sort of draw a couple of diagrams. So this is kind of the situation from above. So the car is going this way around the curve, and the radius of the curve is given by 61 meters per second. And then we're gonna draw our free body diagram, but like from behind the car. So the car's gonna go that way. But yeah, our free body diagram is from the perspective of behind the car. So we have our weight force, normal force up. And then we have, so the center of the circle is kind of that direction from this behind the car vantage point. So we have, that's the direction our static friction force needs to be. Okay, cool. Now we can do our sum of forces equation. So the y direction, the net force is 0 because it's not accelerating in y, and it's normal force in the positive y minus the weight in the negative y. And then for x, so this is circular motion, uniform circular motion. So we have this centripetal acceleration again, remember, and then this equals the static friction force. And we just did this, but as a reminder, the static friction force is v squared over r. Or sorry, man, the centripetal acceleration is v squared over r, not the static friction force. Okay, so for the first part, it asks just what the force is, and we have an equation right here. So let's see. The force of static friction is mass times centripetal acceleration, which is mv squared over r. Let's just calculate that. Good thing we found what the mass was. 1,092 kilograms times 13.4 meters per second squared divided by 61 meters. That gives us a frictional force of, I'm going to round a little bit, but 3,210 newtons for the static friction force. And then the next part, maybe I'll label these A and B. Part B asks for the coefficient of static friction. It asks specifically for the minimum coefficient. So, that just means that anything bigger than that value would assure that it's enough friction to go around the curve. US. So the friction force is the coefficient of static friction times the normal force. We know this, we want that, and then you can get this normal force really quickly if we go back to our sum of forces equation in the y direction. We add that weight to both sides and we just see that the normal force is equal to the weight. So let's plug that in real fast. F times the weight, but we want to solve for mu(s), so we're going to divide the weight on both sides. So we end up with the friction force divided by the weight equals the coefficient of static friction. So 3,210 newtons over 10,700 newtons. And that gives us a coefficient of static friction of 0.3. And again, we know this is the minimum, because that is like the kind of the only thing we could solve for at this point, because we see that the necessary friction force is this value. So that's the minimum friction force necessary to make sure the car doesn't fly out when it's traveling at that speed with that radius of a circle. And then we know that the friction force is, and this would be the maximum. The friction force is the coefficient of static friction times the normal force. And so any value bigger than this would just give us a bigger value of static friction, which is totally fine because that would, again, keep someone from sliding out of the circle. Okay, so that is everything for this lecture. Have a great day.